Welcome back. Hopefully now you're starting to get those sum to product and product to sum identities under your belt. Now we're going to look at an application of one of those sum to product identities. And in this problem, we're looking at trying to find out when these two waves would cancel each other out. When would cosine of 5x and negative cosine of 2x, when would they cancel each other out? This is always an important thing. If you think into chemistry, when you look at those electron slit experiments, you end up having interference patterns. That's where those waves are canceling each other out. And so here we're looking at some basic waves, not quite as complicated as when you're looking at a whole bunch of little atoms running around at each other. We're just looking at two waves, and we want to see when do these two waves annihilate each other. So that's why we want to solve this equation. In its current form, it's really a pain in the butt to solve. Even if you set them equal to each other, when is cosine 5x and cosine 2x, when are they equal to each other? That would be a bit of a pain in the butt to sit down and try to work out. But by using a sum to product identity, we can transform it into a product. Then we'll have a product equal to 0, and our great friend Zupf, or as you may have heard him, the zero factor property, if you're one of those snooty people, we can then use that to solve the equation. The key here is we just use the right sum to product identity. So here we're dealing with a difference of cosines. And we have the one we want. Cosine x minus cosine y will be equal to 2 sine x plus y over 2 sine x minus y over 2. We then plug in our 5x and our 2x. So okay, we're going to have 2 times the sine of 5x plus 2x over 2 times the sine of 5x minus 2x over 2. That's going to be equal to 0. Do a little bit of simplifying. We get 2 sine 7/2 x times sine 3/2 x equals 0. Well, the 2 that's over there, we can just get rid of that. Just divide by it. And now, by Zupf, we got it. Sine 7/2 x equals 2. Sine 3/2 x, sine 7/2 x equals 0. Sine 3/2 x equals 0. Now we set about solving those two equations. Well, 0 is a quadrant value for the sine, so I'm going to draw in my unit circle and realize again that sine is 0 at 0, 2 pi, and so on. Anything that's coterminal with that. And also at pi and 3 pi and so on. Anything that's coterminal with that. So we're going to be looking for all the solutions where 7/2 x is one of those angles. And so we would set 7/2 x equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and 7 pi. And you say, what? Why are we going all the way up to 7 pi? Well, generally speaking, when we're solving an equation like this, we're looking for all the solutions where x is between 0 and 2 pi. But our angle is not x anymore, it's 7/2 x. So to go from x between 0 and 2 pi, we'd have to multiply by 7/2. That would give us that we're looking for all the values of 7/2 x that fall between 0 and 7 pi. So hopefully now you see why we have to go all the way up to 7 pi. At this point, we want to solve the equation. So we want to get rid of the 7/2. We can accomplish that pretty easily by dividing either by 7/2 or multiplying by the reciprocal, 2/7. I think multiplying by 2/7 is probably easier. And we distribute through. And so we get these 8 solutions. 0, 2 pi over 7, 4 pi over 7, 6 pi over 7, 8 pi over 7, 10 pi over 7, 12 pi over 7, and 2 pi. But that was just the sine of 7/2 x equals 0. We still have the other equation, sine of 3/2 x equals 0. So again, it's a quadrant value. sine 0 at each of those different values. And you have to ask yourself, well, 3/2 x, how far will I have to go? You may want to take a moment and see that this is the case, that we have to go up to 3 pi. Anything beyond that would be too big, would lead to an x value that's bigger than 2 pi. And then we say, well, let's multiply by 2/3, and that gets us the answers 0, 2 pi over 3, 4 pi over 3, and 2 pi. You can see two of these, the 0 and the 2 pi, are duplicates. So then we take all those answers, the ones we got for the sine 7/2 x over 2, and the sine 3/2 x over 2, and we put them all together. So it turns out between 0 and 2 pi, there are 10 different solutions to this equation. 10 different solutions. And that's just between 0 and 2 pi. Now, to help you understand and appreciate a little bit of what we've just done here, let's look at a couple of graphs. So here I have graphed my two functions. The purple one is the graph of y equals cosine of 2x, and the blue one is the graph of y equals cosine of 5x. Now our equation was cosine 5x minus cosine 2x equals 0, but we could easily rearrange that equation to be cosine 5x equals cosine 2x. So what we have found is every point between 0 and 2 pi where these two equations. So if we look now at the graph to see where those two curves, cosine 2x and cosine 5x, intersect each other, we'll mark each of those points. And if you look in closely at those, we see the first one's there at 0. The next one, which is a little bit smaller than 1, if you go and compute 2 pi over 7, you'll find out you have an answer a little bit smaller than 1. The next one would be 4 pi over 7. And again, you can see roughly that's between 1.5 and 2. The next one would be 2 pi over 3. And you can go so on with each of our solutions all the way through to find those 10 points of intersection. If there's any background noise, please just ignore it. My son's running around cooking himself some food here at 11 o'clock at night. Now, that's the graph for cosine 2x and cosine 5x. The next graph I have here is actually the combination of those two waves, the cosine of 5x minus the cosine of 2x. Now the scale on the x-axis doesn't line up exactly, but you can see now that each of the times that is 0 lines up pretty much with the times above, where the two graphs, cosine 2x and cosine 5x, are in fact equal to each other. Okay, and so you can see kind of the result there. Hopefully this helps you out, makes things a little bit clearer for you about why you may want to solve this kind of equation, why it is that you may want to solve this kind of equation, and a little bit of a better visual picture of what it is that you actually are finding when you work through that trick. But a good video would be remiss if we did not have a problem for you to turn in. So your problem is actually a little bit less work than the problem that we did. We're going to be dealing with sine 5x plus sine x equal to 0. You're going to want to use the appropriate sum to product identity and then kind of go from there. Okay, and you'll end up, I believe, getting somewhere between 5 and 6 different solutions for this problem here, between 0 and 2 pi. If you have any questions, again, please don't hesitate to contact me, ask, and good luck.